Problem quiz 5 involves weak acid equilibrium. So we're going to see how that can be played out in a problem by using this practice problem as an example. So we're given that salicylic acid has a certain Ka value for its first acid dissociation. Now I want to mention that in general, if you need to find acid Ka values, there's a table given. This is again under the Chemistry Resources tab on the left margin of the course site. And when you scroll that down, in fact, you can see this is directly under the standard heats of formation that was used in another one of our practice problems. But you can find a table that gives the constants, these pKa values. All right, now what we're given here is the standard acid dissociation reaction. And I'll just remind you, we've been writing this in the lesson as essentially being the reaction of a weak acid with water, and it gives the hydronium ion and the conjugate base as two species that are in solution. So if we're writing the Ka for a given reaction, we'll have the concentration of hydronium ion, the concentration of its conjugate of the conjugate base to our weak acid, and the concentration of the weak acid. Now note that this is equal when we're at equilibrium, so we're implicitly having equilibrium values for each of these concentrations. And that should be distinguished from the initial value of the concentration of the weak acid. So for example, we might say that initially we have a concentration of HA0, and some amount of that is going to dissolve or dissociate in water. Okay, but this will now represent the equilibrium value of it in an ice table. Okay, for each of the things that it produces, however, it starts off with 0 concentration and it adds this amount. So when we write out this equilibrium expression, what we're going to have is our equilibrium values for the two concentrations. So we'll have X times X, and in the denominator we'll have the initial concentration of HA minus X, but this is just the HA at equilibrium. Well, in this particular problem, we're going to simplify things a little bit because we're given what the equilibrium concentration of the undissociated acid is. It's 0.02 molar. So in other words, this is just going to be x squared over whatever that equilibrium value of this undissociated acid is. And what we're asked to find is the pH of the solution. So to find the pH, we know that pH is related to the concentration of the hydronium ion via this expression. And I know this looks a little bit forbidding because it's a negative log, but your calculator should be able to calculate those logs. So what we're going to need to do is first find this concentration, and once we've found it, then we can plug it in to this formula to get the pH at the end. All right, so how does this work? Well, our Ka value is 1.07 times 10 to the minus 3, and that's equal to x squared divided by the equilibrium concentration of HA, which is 0.02. So now if I multiply both sides by this 0.02, so I'm going to put 0.02 multiplying over here and 0.02 multiplying over here, I will end up with 2, I shouldn't put an equal sign, there's going to be 2.14, right, times 10 to the minus 5 is equal to x squared, where x is just the hydronium ion concentration. So now all I need to do is to take the square root of both sides. I find that the hydronium ion concentration in this case is simply going to be 4.63 times 10 to the minus 3rd molar. That's just the square root of this number here. And then in order to find the pH, I would simply plug it into this formula, log base 10 of 4.63 times 10 to the minus 3. And you should get an answer that is something like 2.335. All right, now it may seem I've kept too many digits here, but really this denotes the significant figures in a pH because this number here is related to the exponent. So Our pH in this case is going to be 2.335.